Hi, Assalamualaikum. So we are from Group 3 and we are going to presenting the non-metallic mineral extraction of sand and gravel in Malaysia. Okay, for the group member is Nurul Natasha Najwa binti Muhammad Zahari, Nurul Alia MAISARAH binti Mazmi, Hafizul Ashraf bin Muhammad Zaki Kapis, Muhammad Amin bin Murawi, and IKHZANI bin Samsuri.
Hello and very good day for my groupmate and lecturer. And today I gonna talk about application that we use to management of non-metallic minerals, specifically sand and gravel. Unlike metal ore, these industrial minerals are high volume resources essential for construction and infrastructure. However, their extraction often competes with other land uses, making spatial precision critical. Uh, for to analyze this resource, I utilize QGIS as my primary desktop GIS. QGIS is ideal for this because it handles the vector data needed to the map land surface deposit commonly associated with sand and gravels. In this project, I use QGIS to overlay geological maps with satellite imagery, allowing me to identify potential extraction zones and calculate the surface area of these non-metallic deposits effectively. For the web GIS component, I selected QGIS Club QOR or QGIS to web. Managing non-metallic minerals require coordination between various agencies such as Land Office and Environmental Department. By publishing our QGIS project on the web, we created an accessible interface where stakeholders can visualize the distribution of sand and gravel sites without needing specialized software or technical training.
So I'm Nurul Natasha Najwa and my number is E248325. So for technical demonstration, first QGIS version 3.44 was downloaded and installed. After that, a new project was created in QGIS to start the GIS workflow. Next, OpenStreetMap was added as the base map. The map view was then zoomed to Malaysia and the area of interest was defined to include all states in Malaysia. After setting up the base map, Malaysia's state boundary data was downloaded and imported into QGIS. This state boundary layer was used as the main spatial reference for the mapping process. Then, the attribute table of the state boundary layer was opened. Sand and gravel data for each state for the year 2017 were obtained from the Malaysia Government Data Catalogue. The data were prepared in Microsoft Excel format before being added into QGIS. New fields were created in the attribute table and the sand and gravel value from Excel were entered and linked to each state. Finally, the attribute table was updated and saved. Next, a choroid map was created to visualize sand and gravel distribution by state. Graduated symbology was applied to represent different data range, and map elements such as legend, label, and scale bar were added to improve map readability. Green color state represent higher sand gravel values, indicate greater availability or production. Pink color state represent lower sand gravel value, showing limited availability or lower production levels. Several states in Peninsular Malaysia are shown in green, suggesting relatively higher sand and gravel data compared to other regions. In East Malaysia, the distribution is mixed with some states showing moderate values, while others remain low. In addition, the Quick OSM plugin was used to extract OpenStreetMap features related to sand and gravel. The key natural with the value sand and the key surface with the value gravel were applied. This Quick OSM layer were then overlaid with the sand and gravel map to provide additional spatial context. After that, the QGIS web plugin was used to create an interactive web GIS map. Interactive functions such as zooming, layer control, and pop-up information were enabled to allow users to explore the map more easily. Finally, a static color flat map of sand and gravel data for the year 2017 was produced. This map clearly showed the variation in sand and gravel value between states, allowing easy comparison across Malaysia. Differences in distribution can be visually identified based on the color variation on the map. In addition to the static map, an interactive WebGIS was also developed. The WebGIS provides better accessibility and interaction, allowing as to zoom, toggle layers, and view attribute information for each state. Overall, the final outputs demonstrate how GIS can effectively integrate government data and open source spatial data to support sand engraver resource, visualization, and analysis.
Assalamualaikum and hi, my name is Nurul MAISARAH with number E248323. Our group presentation focuses on the use of GIS and WebGIS to analyze an environmental and spatial issue. My individual area of interest is non-metallic mineral extraction of sand and gravel in Malaysia for the year 2021. Sand and gravel are important non-metallic mineral widely used in construction and infrastructure development. However, excessive extraction can cause riverbed erosion, habitat destruction, and environmental degradation. Therefore, mapping sand and gravel extraction spatially is important for monitoring and sustainable resource management. The study area covers Malaysia at the state level. The sand and gravel extraction data for 2021 was obtained from data.gov.my, while administrative boundary data was obtained from GADM. OpenStreetMap was used as the base map. First, Malaysia's state boundary layers were added into QGIS. Then, sand and gravel extraction data for the year 2021 was prepared and joined to the state boundary attribute table. A choropleth map was created using graduated color symbology. Darker colors represent state with higher sand and gravel extraction, while lighter colors represent lower extraction levels. These methods help to clearly compare extraction intensity between states. This map shows the spatial distribution of sand and gravel extraction in Malaysia in 2021. We can observe that some states show higher extraction intensity, which is likely influenced by factors such as urban development, construction demand, and proximity to river system. States with lower extraction may have fewer development activity or stricter environmental control. Quarry and surface gravel locations obtained from OpenStreetMap using QuickOSM were overlaid on the extraction map. These point and polygon features show that sand and gravel extraction activities are commonly located near river system, coastal areas. This spatial relationship support the importance of GIS in identifying potential environmental impact zones. To enhance accessibility and interactivity, the map was exported into a WebGIS platform using the QGIS to Web plugin. This allows users to zoom, pan, and click on each state to view extraction data iteratively through a web browser. This is the WebGIS interface. Users can explore the map dynamically, view attribute information, and better understand spatial patterns without using desktop GIS software. This is useful for decision makers, researchers, and the public. In conclusion, GIS and WebGIS are powerful tools for analyzing and visualizing sand and gravel extraction activities. The 2021 extraction map highlights spatial differences across Malaysian states and provide useful insight for environmental monitoring and resource management. This project has improved our understanding of GIS workflows, spatial analysis, and web-based mapping. Through this project, I learned how to process spatial data, create choropleth maps, and publish interactive web GIS. These skills are important for future application in environmental science and geoscience fields.
We have Sabah, we have 526122. And for the Sarawak, we have 622757. And at Johor, we have 4376955. At Malacca, we have 366038. And for the Pahang, we have 3207755. At Selangor, we have 421665. At Terengganu, we have EFT22837040. While at Kelantan, we have 455141. In Perak, we have 76327775. At Kedah, we have 972218. At Perlis, we have 0. Meanwhile, in Pulau Pinang, we have 472000. Just for me. I'm gonna pass up to our next presenter.
For my part, I will present the GIS workflow for non-metallic mineral extraction of sand and gravel in Malaysia for the year of 2019. First, I started with the attribute table. The data were obtained from data.gov.my, which provides information on sand and gravel extraction by state in Malaysia. Before inserting the data, I created a new dataset called non-metal to store information related specifically to non-metallic mineral extraction. Based on the dataset, several states such as Perlis, Wilayah Persekutuan Kuala Lumpur, Wilayah Persekutuan Labuan, and Wilayah Persekutuan Putrajaya do not have recorded data and non-metallic mineral extraction. Next, I created a choropleth map to visualize the extraction intensity. The map used 5 shades of purple, where lighter color represents lower extraction values and darker colors indicates higher extraction. The ranges from 0 up to 37 millions, allowing clear comparison of sand and gravel extraction levels between different states. After that, I managed the map layers. The layers include land use underscore quarry underscore Malaysia, which shows and labels quarry location by state. The extraction of non-metallic mineral layer display as a choropleth map and OpenStreetMap as the base map. Finally, I generate a web GIS output using the QGIS2 web. After installing that and following the provided instruction, I exported the map as an interactive HTML file. The final web map allows users to interact with the data, view quarry location, and observe the spatial distribution of sand and gravel extraction in Malaysia for 2019. And that concludes my individual presentation. Thank you.
Assalamualaikum, my name is IKHZANI bin Samsuri. My metric number is E2483127 and I will be presenting data for non-metallic minerals extraction of sand and gravel in Malaysia on 2017. Firstly, the relevant vector dataset was loaded into QGIS and verified for geometry attribute consistency and analyzing focus on attribute representing extraction quantities of sand and gravel. Next, the data were symbolized using graduated symbology. A color-left mapping method was applied where extraction values were classified into 5 classes based on numerical range. This classification allows clear differentiation between low, moderate and high extraction levels. A sequential color ramp from light to dark green was selected to represent increasing extraction intensity. Lighter shade indicates lower extraction values, while darker shade represent higher values, ensuring intuitive visual interpretation. The map was overlaid on an OpenStreetMap base map to provide spatial reference, including coastline, state boundaries, and major geographic features. This improved the accuracy and clarity of spatial orientation. Layer order and visibility were adjusted to ensure the extraction layer remained visually dominant without obscuring base map details. Finally, the map layout was reviewed to ensure it meets cartographic standard and suitable for output, presentation and potential web GIS publication. Overall, the final result demonstrates effective use of data management, attribute classification, symbology design, and GIS visualization technique to produce a clear and technically sound spatial output.
For this part, I will be explaining the application of GIS to an environmental and spatial problem. As geoscience student, we choose non-metallic mineral extraction, specifically sand and gravel quarries, because it is closely related to our course and future field of work. Sand and gravel quarrying is important for construction and infrastructure development in Malaysia. However, if it is not properly managed, quarry activities can cause environmental problems such as land degradation, soil erosion, river sedimentation, and loss of vegetation. This is where GIS becomes very useful. Quarry locations are special in nature, meaning their impacts depend on where they are located and how they change over time. Using QGIS, we map quarry locations for different years, which are 2016, 2017, 2018, 2019, and 2021. Each year was displayed as a separate layer, allowing us to visually compare changes in quarry distribution over time. Through this GIS visualization, we can identify areas with high concentration of quarry activities and regions that show consistent extraction across multiple years. These spatial patterns help highlight areas that may be more exposed to environmental risks and therefore require closer monitoring or better management. Overall, GIS plays an important role in supporting sustainable resource management by helping geoscientists and authorities make informed decisions related to quarry planning, environmental impact assessment, and land use management. And that's all for my part. Thank you.
This section presents a comparison and evaluation of desktop.js and web.js based on usability, scalability, and accessibility. In terms of usability, desktop.js such as QGIS offer advanced tools for spatial analysis and data processing, but it requires technical skill and user training. Web.js provide a more user-friendly environment, allowing users to interact with maps easily with minimal technical knowledge. Regarding scalability, desktop.js is generally limited to individual computer and is constrained by hardware capacity. In contrast, web.js platforms are more scalable as they allow multiple users to access and explore spatial data simultaneously. In terms of accessibility, desktop.js requires software installation and is mainly used by JS professionals. Web.js is more accessible because it can be accessed through web browser, enabling wider public access and easier information sharing. However, there are limitations in both systems. Desktop.js has steep learning curve and limited accessibility for non-expert users, while Web.js has limited analytical capability and depends on internet connectivity. For potential improvement, integrating more advanced analysis function into Web.js platform will enhance their functionality. Improving system performance, data security, and user interaction will also increase the effectiveness of Web.js. Overall, combining desktop.js for detailed analysis and Web.js for visualization and sharing provide the most effective JS approach.
This project also demonstrates several important digital skills showcase. Firstly, we applied spatial data handling skills by managing vector datasets and attribute-based environmental data within QGIS. Secondly, we demonstrated attribute table analysis skills by interpreting numerical data and identifying key variables for mapping and comparison. We also applied cartographic visualization skills through the use of Korolev mapping techniques, including appropriate classification and color selection. In addition, we developed spatial interpretation skill by analyzing geographic patterns and relating extraction intensity to environmental and developmental factors. Finally, the GIS outputs created in this project are suitable for future web GIS publication, allowing the information to be shared interactively with a wider audience. Overall, this project highlights our ability to use GIS tools effectively to analyze and communicate spatial environmental information.
To conclude our presentation, this project demonstrates how GIS can be effectively applied in mapping and analyzing sand and gravel resources, which are important materials in geoscience. By integrating spatial layers such as administrative boundaries, land use and potential resources zone, GIS allows us to visualize the distribution of sand and gravel more clearly and support better planning and environmental management decisions. Throughout this project, we gain valuable hands-on experience using QGIS, including data collection, attribute editing, thematic mapping, and developing a web GIS platform. This process helped us to better understand how GIS concepts are applied in real-world resource assessment and improvement our technical skill as well as our spatial analysis and map interpretation abilities. So for future improvement, we suggest integrating more detailed geological information and official quarry or mineral resource datasets to increase data accuracy. In addition, apply advanced GIS analysis such as stability modeling and 3D visualization will further enhance sand gravel assessment and support more sustainable resource management.